All right, let's look at the theorem 2, tangent theorem. Right, so it says that the line intersects a circle at point A, at least, and if actually the L is tangent to the circle at A, if and only if OA, always the center of the circle, is perpendicular to the line L. Right? So since this is if and only if, we have to do both implications. So let's prove the first implication. All right, so let's assume that L is tangent to the circle at point A. All right, so we want to show that segment OA is perpendicular to L. All right, so I'm going to list all possibilities. So we say segment OA is not perpendicular to L, or segment OA is perpendicular to L. So this is just listing all possible cases, so I'll just say all cases. Alright, then to 3. Alright, why not pick on the first case? Assume that the segment OA is not perpendicular to L. Right, so this is case 1. Alright, so in this case, OA right here is not perpendicular to A, which means that we can find another point. So let's say 4. Alright, so there must be, there exists another point B on the line such that OB is perpendicular to the line L. So this is justified by existence of perpendicular from exterior point. In this case, exterior point is the center O. So we should be able to find, say, another point B here, such that it doesn't look like it, but such that this is going to be perpendicular. So perpendicular here and a perpendicular there. Maybe I should use a different color there. Right, so I'll use green here. So perpendicular here and a perpendicular there. Alright, so then we're going to construct another point. So I'm going to construct, construct another point C on the line L, such that, alright, so we have, let's see, the between this condition is A, B, C, and we want AB is equal to CB. Right? So this is just a segment construction theorem. I'm just going to say construction theorem. Right? So I'm going to construct another point C here, so that the length here is the same as length there. Right? Then I'm going to look at the two triangles right here. Alright, so first I'm going to just say BC, OB, or BO, doesn't matter. We know that the, maybe I should say, I'm going to say OB. OB is, of course, congruent to segment OB itself because of the reflexivity of congruence. Reflexivity. Right? Then we can say triangle ABO is congruent to triangle CBO. BO. Alright, so this is by side, angle, side. Alright, so side, because AB equals CB, so it comes from 5. And angle, because they are perpendicular, so B is perpendicular, so it's a line 4. And OB is just by reflexivity, so we have that. Right? So we established that these guys are congruent to each other. Right? And which means that here 8. If you look at the OC, which is going to correspond to OA, which is the radius, right? So we have OC is congruent to OA, which is a radius. This comes from, let's see, so this is corresponding parts of congruent figures, right? Then 9, which means that if OC is equal to R, C is going to be on the circle, right? So on the circle as well. So a circle, right? And this is going to be a contradiction because L is supposed to be a tangent line which touches the circle only at A, but we found the C, which is on the line and on the circle at the same time, which is different from A. So this is the contradiction, and it contradicts the fact that L is a tangent line, right? So that comes from number 8. Alright, so since this is a contradiction, so last line, maybe I'll do it here. So last line, number 10. So therefore, we know that OA, segment OA has to be perpendicular to line L by rule of elimination. So which is case 2. Alright. So that's the proof of one direction. Alright, so I'm gonna do the other implication as well. Alright, I'm gonna have to erase this first. Alright, let's look at the proof of the other implication. Alright, so let's assume that the segment OA is perpendicular to L. Alright, and we'll try to show that L is the tangent to the circle at A. Alright, so 2. So there are two possibilities. L is not tangent to the circle at A, or is tangent. Right? So those are all possible cases. So I'm just gonna say all cases. Right, and 3, I'm going to assume, what if it's not tangent? So assume that L is not tangent. Right, so this is case 1. Right, case 1. Right, which means that it's going to have another intersection with the circle, so I'm going to just draw it like this. Right, so here's L. So since it's not tangent, so there's going to be another intersection point, so I'm going to call this point B. So 4. So we know that there exists another point B on the line and circle. So say circle centered at O, radius R, such that this is different from A. Right? So this just comes from 3. All right. Then if you look at this triangle right here, all right, so we already know that this is perpendicular, so we have a perpendicularity here and here, right? So since A and B are on the circle, we know that the 5 OA is equal to OB, which is the radius, right? So this comes of the fact that B is on the circle, so you have 4, right? And 6. This means that we know that the measure of the angle, OBA is equal to measure of the angle OAB, because we have isosceles triangle. So this triangle right here is an isosceles triangle. So I'm using the number 5. Actually, number 5 is line before. Maybe I'll just say isosceles triangle theorem. I have that. And on top of that, we can actually say, since OAB is 90 degrees, so this is going to be measure 90 here, right? Which is actually a contradiction. Maybe I'll do this. How about this? All right. So this is equal to 90. How about this? 8. Measure of the angle OBA plus measure of the angle OAB, and plus measure of the angle, actually, let's see, angle AOB, right? We know that this is less than 180, right? This is by Sakari-Legendre theorem, saying that angle sum of a triangle cannot exceed 180, right? But using line 6, we know that the measure of the angle OBA plus measure of the angle OAB is already 90 plus 90, so it's 180, and plus there's a non-zero measure at the angle AOB. So we know that this is going to exceed 180, right? So I'm using line 6, but this is a contradiction with line 8, right? So therefore, we have a conclusion. We know that assume L is not tangent, so therefore L is tangent to the circle at A by rule of elimination. This is again case 2. Right? So this will establish the if and only if statement up here. So if L is tangent, the point of contact always make a perpendicular, I should say radius at the point of contact makes 90 degrees with the line tangent line there. All right, that's it. I hope that this was clear.